Sklearncovarianceledoitwolf. Description: explain in detail. The Ledoit-Wolf shrinkage estimator is a method for estimating the covariance matrix of a dataset, particularly when dealing with high-dimensional data or limited sample sizes. This method addresses the issue of sample covariance matrices being highly sensitive to noise and outliers, leading to unstable and unreliable results. The Ledoit-Wolf estimator combines the sample covariance matrix with a scaled identity matrix, shrinking the sample covariance towards a diagonal matrix. This shrinkage helps to regularize the covariance estimate and improve its stability. Inputs: X, a 2D array of shape n samples. N features representing the dataset. Each row corresponds to a sample, and each column represents a feature. Assume centered, a Boolean value indicating whether the data is assumed to be centered. If true, the data will not be centered before calculating the covariance. Outputs: shrinkcov, a 2D array of shape n features. N features representing the estimated shrunk covariance matrix. Shrinkage, a float value representing the amount of shrinkage applied. This value ranges between 0 and 1, with 0 indicating no shrinkage and 1 indicating complete shrinkage to a diagonal matrix. Steps: calculate the sample covariance matrix of the data. Calculate the optimal shrinkage coefficient based on the data and the sample covariance matrix. This coefficient is determined to minimize the expected squared error between the estimated covariance and the true covariance. Shrink the sample covariance matrix towards a scaled identity matrix using the optimal shrinkage coefficient. Metrics: mean squared error. This measures the difference between the estimated covariance and the true covariance. Frobenius norm: this measures the distance between the estimated covariance and the true covariance. Visualization plots: heat map of the covariance matrix. This allows for visual inspection of the relationships between variables. Scatter plots of variables with highlighted correlations. This helps to visualize the strength and direction of relationships between variables. Fine-tune parameters: assume centered, a Boolean value indicating whether the data is assumed to be centered. Default is false. Uncertainty methods: bootstrap resampling. This technique involves repeatedly drawing samples from the original dataset, with replacement and calculating the covariance matrix for each sample. The distribution of these estimates can be used to quantify the uncertainty in the estimated covariance. Bayesian methods: these methods treat the covariance as a random variable and use prior information to estimate its distribution. This can help to reduce the impact of limited sample size and improve the robustness of the estimate. Challenges and fixes. Challenge 1: high dimensionality of the data when dealing with datasets with a large number of features. The sample covariance matrix can become highly unstable and unreliable. Sample use case that resulted in challenge 1: a dataset with 100 features and 100 samples might result in an unstable sample covariance matrix. Fixes to challenge 1: the Ledoit-Wolf shrinkage estimator helps to address this challenge by regularizing the sample covariance matrix and reducing its sensitivity to noise. Challenge 2: outliers in the data. Outliers can have a significant impact on the sample covariance matrix, leading to biased estimates. Sample use case that resulted in challenge 2: a dataset with a few outliers in one or more features can significantly affect the sample covariance matrix. Fixes to challenge 2: the Ledoit-Wolf shrinkage estimator helps to mitigate the impact of outliers by shrinking the sample covariance towards a diagonal matrix, which is less sensitive to outliers.